Hello everyone, I'm Gu Kyung Kwon, a PhD student from Georgia Tech. Today I would like to talk about our paper titled Backpropagated Gradient Representations for Anomaly Detection. In this paper, we tackle the problem of anomaly detection. Anomaly can be defined as data whose classes or attributes differs from training data. For instance, images with different class or images with different conditions can be anomalies to train networks. We propose an anomaly detection algorithm to successfully detect such anomalies and ensure the robustness of machine learning algorithms. Most of existing anomaly detection approaches utilize activation-based representations, such as reconstruction adder. These activation-based representations are utilized to characterize how much of the input does not correspond to the learned information. On the other hand, in this work, we propose the utilization of backpropagated gradients as representations to capture anomalies. Intuitively, anomalies require more drastic updates on neural networks to fully represent them compared to normal data. Therefore, we use backpropagated gradients to characterize how much model update is required by input to detect anomalies. Our contributions can be summarized as threefold. First, we propose utilizing backpropagated gradients as representations to characterize anomalies. Second, we validate the representation capability of gradients for anomaly detection in comparison with activation through comprehensive baseline experiments. Finally, we propose an anomaly detection algorithm using gradient-based representations and show that it outperforms state-of-the-art algorithms using activation-based representations. To further elaborate what gradient-based representation characterize and why they can be more effective than activation-based representations, we provide geometric interpretation of gradient-based representations. Assume that we have an autoencoder trained to accurately reconstruct normal images. The reconstructed image forms manifold, and for the simplicity of explanation, we assume that the manifold is a 2D plane. Ideally, perfect reconstruction is achieved when the reconstructed image manifold includes the input image. Now, when an abnormal image X out sampled from abnormal data distribution is given to the network, it will be poorly reconstructed since the abnormal data has not been utilized for training. The distance between X out and its reconstruction X head out is formulated as reconstruction error. When the reconstruction error is backpropagated, the gradient with respect to weights are calculated. These gradients represent required changes in the reconstructed image manifold to incorporate the abnormal image. In other words, these gradients characterize orthogonal variation of the abnormal data distribution with respect to the reconstructed image manifold. This geometric perspective highlights several advantages of gradient-based representations for anomaly detection. First, the gradient-based representations provide directional information to characterize anomalies. Compared to the reconstruction error, which measures the distance information, the gradient captures in which direction the abnormal data distribution deviates from normal data representations. Also, gradients from different layers capture abnormality at different levels of data abstraction. Gradient can be obtained from any layer through backpropagation. And this enables algorithms to capture fine-grained abnormality both in low-level characteristics such as edge or color and high-level class semantics. We also provide theoretical interpretation of gradient-based representation using Fisher kernel. The reconstructed image manifold can be considered as a probability distribution conditioned on decoder weight and latent variables. In this probabilistic manifold, local properties are defined by the geometry of tangent space of the manifold. Fisher kernel can be defined to measure difference between two data points using Fisher score U phi x and f in this formula called Fisher information matrix. We use feature kernel to measure the distance between normal data and the distance between normal and abnormal data. For successful anomaly detection, we expect K out to be clearly distinguishable from K in. The difference between K out and K in is characterized by the last term, which is feature score. We can estimate this feature score using backpropagated gradients, given that the autoencoder is trained to minimize the negative log likelihood loss. Therefore, we use backpropagated gradients to characterize distance between normal data and query data to differentiate abnormality. To further obtain clear separation between gradient from normal data and abnormal data, we propose to constrain gradients from normal data to the tangential space of the manifold during training. In particular, we use gradient loss, which is cosine similarity between average training gradient and then gradient loss from the current iteration as a regularization term during training. This constraint will result in tangential gradient from normal data, while orthogonal gradient from abnormal data, and make them separable. Our proposed anomaly detection algorithm, GradCon, utilized the combination of reconstruction error and gradient loss as an anomaly score to detect anomalies. To validate the effectiveness of gradient-based representation, we perform comprehensive baseline experiments using CIFAR-10 dataset. We compare 4 different models for abnormal class detection. We use reconstruction error, latent loss, and gradient loss separately as anomaly score and report the performance. First, we compare convolutional autoencoder and convolutional autoencoder trained with proposed gradient constraint. The highest average AUROC performance from the gradient loss of the CAE plus grad highlights the effectiveness of the gradient constraint. Second, we compare the convolutional autoencoder and the variational autoencoder trained with the latent constraint. From the latent loss of VAE, higher average AUROC performance is achieved, but the performance of the reconstruction error from VAE is sacrificed compared to the reconstruction error from CAE. This shows that using combination of multiple activation-based representation face limitations in improving the performance. Finally, we compare VAE and VAE trained with gradient constraint to highlight complementary features from the gradient constraint. Gradient loss from VAE plus grad achieves improved performance in comparison with VAE. Also, the performance sacrifice from the latent loss is marginal in VAE plus grad. These show that gradient representations can provide complementary features to the activation-based representations. We use gradient constraint to perform abnormal condition detection and report the performance. The goal of this task is to detect whether the images are affected by challenging conditions. As shown in the figure, gradient loss from convolutional autoencoder trained with gradient constraint outperforms outer baseline consistently throughout different challenge levels and conditions. We compare our proposed method GradCon with state-of-the-art anomaly detection algorithms in CIFAR-10, MNIST, and Fashion MNIST dataset. While all the existing algorithms are based on activation-based representations, only GradCon utilizes gradient-based representations. We show that GradCon achieves state-of-the-art performance in terms of AUROC and F1 scores. Finally, GradCon is simple and computationally efficient. GradCon does not require adversarial training or autoregressive models. This significantly reduces the number of model parameters and computations. GradCon achieves 1.9 times faster average inference time than the state-of-the-art method, GPND. Also, it requires at least 27 times less number of model parameters compared to other state-of-the-art algorithms. In conclusion, we propose using a gradient-based representation for anomaly detection by characterizing model behavior on anomalies. The proposed anomaly detection algorithm GradCon achieves state-of-the-art performance with significantly less number of model parameters. Finally, using training strategies such as adversarial training or probabilistic modeling on gradient-based representations remain for future work. More details can be found in our paper, and thanks for your attention.